Okay, so section 3, we're talking about the hazards of nuclear power plants, right? So we need to know what hazards nuclear radiation presents to human beings, where those hazards come from, the natural or man-made versions of that, how we deal with radioactive waste, and some examples of how when things went bad, such as Chernobyl, 3 Mile Island. And last, we're going to talk about safety procedures and precautions that are taken for a nuclear power plant, because as we learned last section, although it's pretty safe and it's pretty reliable, accidents do happen, and a lot of times they're human faults, not necessarily process fault, and humans just make mistakes, so it's better to have safeguards in place than none. So first thing to talk about is radioactive emissions. So we learned about fission, and fission is when an atom is going to be split into halves. Now this isn't like a 50%, 50% half, it just means it's broken up into 2 or more different pieces. And those 2 or more pieces are usually radioactive themselves. All right, so to become radioactive, they have to be an isotope, so they have more neutrons than is necessary. Well, atoms typically don't like having anything like that. They want to have the appropriate amount of neutrons to match the amount of protons that they have. So in response to having extra neutrons, what they end up doing is flinging off those extra neutrons, and that is what we call radiation, at least one type of it. So when the uranium breaks into 2, it'll make the halves, which can be imperfect halves, but depending on what they make, they'll have extra neutrons, and those extra neutrons will fly off. And that's why it's dangerous, because neutrons are very small, very fast. They can damage things like our DNA, and if you know, remember back to biology, DNA is how we exist. If that gets damaged, then we get things like cancer, or if we're exposed long enough, we can die. All right. So the amount of damage radiation can do depends on a couple of things. So first is the amount of radiation present. So if you're not around radiation, it can't really harm you. But it's more important to measure how much radiation has been absorbed, right? So if you're in a bunch of radiation, but you're in a special suit that blocks all the radiation from being absorbed, you're not going to get hurt, right? So the first measurement is going to be a Curie. All right, so that's just a measure of how many particles get released off of a radioactive substance. The absorption measurements are going to be 2, a big and small one. So grays are the smaller or low dose radiation absorption, and sieverts are going to be the large dose. All right, so if you absorb too much radiation, you damage DNA, you prevent cell division, you prevent lots of things from happening that are vital for your body to function. So it's really not good, and eventually you can get radiation sickness and start vomiting, and it's really bad. You don't want that. So where does radiation come from? Well, all the time we're experiencing radiation. We get radon radiation exposure from the Earth's crust. We get cosmic rays from space, X-rays from medical use and the sun. Even some of the products we use contain radiation in them in low amounts. But the good news is that 1, they're not very high amounts of radiation, and 2, our bodies do have the ability to repair the damage from them. It's only when we absorb too much and too much damage is absorbed for our body to repair that it becomes a problem. So as radioactive waste decay, they're going to eject those halves like we were talking about. And there is this concept of a half-life that follows, right? So a half-life is the amount of time it takes for half of a radioactive substance to decay. And it's going to decay into a non-radioactive substance. And that changes from isotope to isotope. It really depends on which one you're talking about. Some have longer ones, some have shorter ones. Now, it's really important to take advantage of that or use it to our benefit to put away the nuclear radiation waste so it doesn't expose to anybody. But more importantly, like we were talking about in other sections, nuclear is considered a renewable resource because we can take advantage of reprocessing. So just by doing the fission itself, we can generate more nuclear fuel in the form of plutonium, which can then be split across 2. So doing uranium nuclear radiation energy production will produce plutonium, and then that can be recycled and broken apart again to make more uranium, which can then make more plutonium. So it's really neat. Here is a graph showing how half-lives work. So we're talking about this CO60, right? So it has a half-life of 5.27 years. And after 1 half-life, we're going to lose 50% of this substance, right? So it's going to go from 100% down to 50% after how many half-lives? 1. In this case, it went from 10 grams to 5 grams. But you need to be careful here, because after another half-life, so after another 5.27 years, it's not going to lose that second 5 grams. It's going to lose half of the 5 grams, so 2.5 grams. So after about 10.5 years, you're going to go from 10 grams of this radioactive CO60 to 2.5 grams, and so on and so forth, until we can't really detect if it's there or not. Here are some other different products that uranium can fission into, right? So some of the halves we were talking about before. You don't need to memorize this. I just wanted you to see all the different things that it could become. So obviously they're not perfect halves. They're just other elements, other isotopes with varying degrees of radiation and varying times for how long the half-lives last. So when we finish with our nuclear fuel, we need to just get rid of the waste, right? So that's called nuclear waste disposal. There is short-term containment and long-term containment. And in short-term containment, they keep the waste inside of little casking tubes to make sure that they finished kind of cooling off and aren't emitting any radiation. Now, usually it's about 10%, and within, not 10%, 10 years, and within those 10 years, about 97% of the radioactivity will have subsided, so that's good. There is also long-term containment, which is, and it's kind of funny because it's a really long time. It's 100,000 year minimum from the EPA. Now, that's one standard, but there's also a different government standard that is for 20 half-lives. And remember that the length of half-lives is dependent on each isotope. So something like plutonium, which has a half-life of 24,000 years, if you want to put it through 20 half-lives of like cool down and waste disposal, that's 480,000 years. Like, who's going to be around to watch the plutonium, make sure no one touches it for 480,000 years? So it's a long time. Now, tanks and casks are how we actually protect and control the nuclear waste. So they are put into these tanks and casks, and they are filled with concrete and steel, and that allows it to contain any sort of nuclear radiation that's going to continue on that we don't want. And they're put into pools of water that absorb the heat and the radiation. So the pools can hold like 10, 20 years of nuclear waste. That's good, except for the fact that we're running out of space in the pools, and they have to be cooling in the pool for a minimum of 5 years, and that's pretty crazy to think about, that something can sit in a pool of water and cool off for 5 years and still have leftover heat and energy. But it's true, right? They have to stay in there. You could move them to different places or bury them underground. There are various spots around the world where nuclear waste is just put into the ground, but that's easier to access. It might leave more radiation to expose to the environment and to people, and that wouldn't be good. So it's always a trade-off of what do we want to do, what's best for right now, what's best for the future, things like that. So over here is some of the tanks with the water, and this fellow here is taking these and putting them down into the cask, and you can see just how much water is. A pretty big pool, and imagine how much water this is. Like, that can absorb a lot of heat, so just gives you an idea of how much heat these things can emit after a period of time. Now, there have been incidents of mismanagement of nuclear waste, both by the United States and the old Soviet Union. It's really bad because, one, it damages the environment. Two, it costs a lot of money to fix. So perhaps the craziest one is when the Russian military just dumped a bunch of radioactive waste into rivers, and rivers flow, and they are water sources and where some organisms live, and it really affected the things living there. Right? There's over 1,000 cases of leukemia tied to that, just one event of just poor stewardship. There's another one, Lake Karachay, where they dumped a bunch of nuclear waste into the lake, and the lake ended up drying up, and dry is not good, especially for nuclear waste, because it becomes this fine powder, and erosion can take up the fine powder and spread it around lots of places, and it did, and it contaminated lots of people. But the best use of our nuclear stuff has been when we changed our nuclear weapons into fuel sources. So that's what I mean when I say megatons to megawatts. So you can dismantle nuclear weapons and take the very highly enriched uranium out of them and dilute it so it's the proper ratio for power plants. And I think that's a better use, right? Thankfully, nuclear bombs have only been used to hurt people twice, but the amount of energy that nuclear power plants generate for us help to improve or save lots of people's lives. So it's a good thing. It's about 10,700 warheads, 270 tons of weaponized uranium or highly enriched uranium. So it's good to see that productive uses of nuclear technology are being used more than destructive uses. That brings us to accidents. So accidents have happened. They do happen for various reasons. 3 Mile Island, which is one of the events that spurred the big protests in the United States, that big dip we saw in Section 1, was because of human error and equipment failure. So they released a lot of curies into the atmosphere, something like 10 million. They closed down the plant. It caused a lot of hysteria. No one was really hurt or anything, but no one has to get hurt to see how bad that could have been, right? So it's understandable to see, okay, maybe I don't want a nuclear power plant by my house. Chernobyl, on the other hand, very famous Ukrainian accident. They were testing some generators and they disabled the normal safety systems. Long story short, all the things failed and there was a meltdown. As you remember, the meltdown is literally the uranium metal melting into the steam and water containment chambers, and so much heat in so little time and so little space causes a steam explosion, and it releases a lot of radiation, kind of 150 million curies out into the atmosphere. And although you can kind of walk around in that area right now, no one's going to live there unless they're crazy. It's not terrible. It's not like everything is just this barren wasteland, but it's pretty abandoned. It's pretty creepy. You can see videos on YouTube of people exploring those places. It's pretty neat, but nobody wants to live there. So as a result of Chernobyl, 2 people were killed in the steam explosion, the workers there. 28 died from radiation sickness. So the amount of radiation they were exposed to ended up killing them. 135,000 people had to be relocated because it used to be a pretty big city and big power plant there. Well, those people can't live there anymore, so they had to move. And about 4,000 cases from contaminated milk and 9 deaths from there. So for what it could have happened, it's not as bad as it might have been, but it's still bad, right? It's a ghost town now and nobody can live there, and it's eerie and it's creepy and it shouldn't have happened, I guess. Human error was one of the main reasons that caused it. Human error is one of the primal reasons that any sort of nuclear facility accident happens. Now, because of these accidents, there's more safety regulations for nuclear power, and they have added these things called passive safety features. So things that don't require any active actions from a person to enable them. So in the Chernobyl case, they had to enable the generators for emergency water pumping to cool down the reactor. And a lot of the passive ones, it happens despite humans being there or not. So the reactor could be melting down, but the passive safety features will enable because of that and doesn't require anyone to do that. So no amount of loss of power, no amount of lack of water is going to allow the meltdown to occur. And that's what we call the 3rd and 4th generation reactors. So places like Fukushima, those were 2nd generation reactors that weren't well protected, that didn't have these safety features that were passive. You can kind of put the blame on the power company for doing that, right? We have the technology to make them much more safe, but they didn't do that. And so people want to blame the process of nuclear energy when really it was a person's fault. Like the people decided not to build a seawall tall enough to withstand a tsunami. People decided not to upgrade the nuclear power plant so that it had passive safety features. So if you really want to blame someone, it's people. That stinks, but humans are like the #1 cause of nuclear power plant accidents, right? It's not the nuclear power plant's fault. It's people failing to do due diligence that causes nuclear power plants to fail. Okay, so the economics of nuclear power, it's pretty much the same price as fossil fuels right now, all things considered, unless like something happens and fossil fuels get really cheap for a little while. But as we know, fossil fuels are finite. They are not renewable. Sooner or later, that's going to catch up. Not in the near future, but sooner or later. Nuclear power plants can last about 50 years, which is pretty impressive. But then after that, they have to be shut down. Sometimes before that, like Fukushima, I don't think they're going to fix that just because of the perception of the public and everything. When you can decommission a power plant, which means to shut it down, because you have to take everything out, remove everything, clean it, absorb the radiation, things like that. But you can also convert it into a regular fossil fuel power plant. So that's really good. Okay, so that is it for section 3. Keep in mind about how half-lives work. Remember about Chernobyl and the accidents. Remember how there are passive safety features, and know about decommissioning a power plant. As always, if you have any questions, go ahead and email me or post onto the Google Classroom forum. Thank you for watching, guys.